How are you guys? It's good to see you. So we are going to do a review of our waves unit for our quiz on Thursday. Yesterday, Monday, you tried to answer some quiz sample questions. Today, I will give you an overview of the entire unit, and tomorrow I'm going to go through and answer those quiz questions for you so that you can have the correct answers. And then Wednesday, you'll do some studying and some organizing, and then Thursday's the quiz. So here we go, our waves unit. What are the properties of the waves? And so think about how we are going to prepare for a test where we're thinking about waves. What are properties of waves? How do they transmit sound and light energy? Those were the two focuses of our unit. How are sound and light waves similar and different? What happens when waves move from air to another material, such as water, a mirror, or cloth? When are waves harmful? How do scientists and engineers use waves for research and communication? To investigate these questions, we used mathematics to recognize patterns in the properties of waves. We used models to compare the properties of various waves and communicate explanations about them. And you did integrate science and technical information as you investigated advances in communication technologies. This screen is something I actually put together when I teach teachers about the unit, and I thought it would be really cool to show you the flow of what we did. And the color coding is related to the types of activities that you did. So number one activity, It's a Noisy World, was an investigation. And remember, that's where we just said, here's decibels, here's intensity, what's the relationship between decibels and intensity? Making sound waves, we had a couple of live performances, thinking about how does sound travel through the air and what are the different properties of sound. We then looked at the nature of sound, discussing what kind of wave it is. We looked at noise-induced hearing loss with that integration between the frequency and the duration, the decibel, the amplitude and the duration. We made a telephone model with activity 5, which you guys loved. Then we compared and contrasted analog and digital technology. Then we looked at the other kind of wave, transverse. We talked about reflection, mirrored surface, refraction, bending through a medium. Comparing colors was that visible light spectrum and the energy associated with frequency. Selective transmission, how do certain materials pass? Are they absorbed, reflected, refracted, transmitted? And then we did a whole reading on the electromagnetic spectrum. Where does the light go? We looked at how we used the thermometer to do a couple of experiments, and then we used the black cloth and the aluminum foil, blocking out ultraviolet light. We looked at sunscreen, and then the personal protection plan I actually left out for you. Instead of you designing a personal protection plan, I asked you to create a design and collect data on an experiment or watch an experiment from activity 14. So let's start with activity 1. My plan here is to go through each activity with you. If you have a giant piece of paper and you want to jot things down, that would be great. If you thinking about how am I going to get this all organized and prepared so that when the quiz comes, then I can be prepared. So It's a Noisy World was what is the range of sound intensities humans can hear? And remember, I passed out those cards, and on those cards, the dot filled in was the intensity of the sound based on that whole area. So intensity has to do with an area. And then here it says this sound, moderate rainfall, was 10 decibels, and it was just one dot out of that whole grid. The vacuum cleaner, if you're 1 meter away, was 70 decibels. So the difference between 10 and 70 sounds like 60 decibels, but that is a different pattern than intensity. So with intensity, we had the relationship between decibels and how intense the sound was. This mathematical concept is patterns. we're looking at relationships between variables. So we learned as the decibels increase by 10, adding 0 to 10, 10 to 20, 20 to 30, I'm adding 10 each time, intensity is multiplying by 10. So at a 0 decibel, the intensity is 1. If I add 10, the decibel at 10 has an intensity of 10. But when I go from 10 to 20, I don't just go up by 10. The intensity is 100. No, sorry. 0 to 20 is 100, right? Because I'm going up by 10 each time. So that relative intensity multiplying by 10 each time. So 10 to 20 is still just a 10 level. So if I look at on my sound levels of common noises, if I look at, so say I'm in a quiet library and the decibels is 40. 40 decibels has an intensity of 10,000. But how much more intense is a conversation? Like, so the library is like, shh, don't be quiet, be quiet. Because if I'm in the library and it's supposed to be quiet and that's about 40, if I'm talking to my friend in a normal conversation, that's 100 times more intense. So that going from 40 to 60 is 40 to 50, 10, 50 to 60, 10, 10 times 10 is 100. So that idea that the relative intensity is that scale that multiplies by 10 each time. And so you have this diagram already filled out in your student notebook. I don't know if you have your student notebook with you or not, but you certainly could add these relative intensities and decibels to that chart if you'd like to. Some of the analysis questions, and you know that I do steal some of the analysis questions when I write quizzes. And so in each activity, and I will make sure to post that the book for you, the PDF of the book. It's on Schoology for sure, but I can post it on your Google Classroom page. Just checking, right? Like when I study, I don't go ahead and write down every question. I say, what is the range of sound intensities that humans can hear from the quietest to one that causes pain? So the range of sound intensities from when humans can hear, so the threshold of hearing is about an intensity of 1. The threshold of pain, if it's 120, it's 1, 2, that's a million, billion, a trillion. So 1 to a trillion of pain for intensity. So you're not necessarily writing things down. You're just looking at the question and you're going, okay, I see that. I have a noise-induced reducing headphones. They reduce by 100 times. And so like you could answer those questions and just look at the answers. You don't have to worry about writing them down. I did find the simulation that was really cool, and I don't want you to necessarily get lost in it, but I will post the link for you. How loud is too loud? It was kind of fun. I think you do maybe need Adobe Flash, and I don't know if you have that, but we'll see if it works. If it doesn't work, don't worry about it. Activity 2, making sound waves. And so when we made sound waves, we were looking at how can we model those, and our vocabulary was frequency, hertz, audiogram, which was this diagram here, compression, rarefaction, and wave. So in a sound wave, the direction of travel vibrates, that's the energy direction, the particles are vibrated parallel. Remember, sound waves need a medium to travel through. They are mechanical waves. And then we use that middle string to model compression waves. And then thinking about this vocabulary, which at this point is so repetitive, hopefully you've got it. I just wanted to take some time and celebrate making sound waves.
Okay, sorry, man. Okay, ready? One, two, 1, 2, ready, go.
Right there. I love you guys. And then, of course, because we had a couple of different musicians, I wanted to take the time to show you some more music. Relax, feel the energy, feel the positive energy. Let your brain absorb some content while you enjoy compression waves. It's beautiful. I really miss the band. So thinking about as you listen to that and you're imagining that those compressions, and you know how sometimes when you are listening to music or you're at a concert or in a place where it's really loud, you can actually feel the vibrations on your body. That's because sound is a compression wave and it's actually vibrating the particles. If the amplitude is high enough, that energy can actually vibrate your cells, and which is so cool. So coming from compression waves and what are the characteristics of sound and how do musical instruments affect the actual wave, then we looked at how your ear, the structure of your ear, collected that information and from your auditory nerve, your optic nerve is your eyeball, your auditory nerve here, how that information was then synthesized and transmitted to your brain for what, to process what it is. And so as that sound comes in, the ear canal, the tympanic membrane is that drum membrane that vibrates when that compression wave hits it. And then remember, we had those little teeny bones in that middle ear, the stapes, the anvil, and the stirrup. Can't believe I remembered that. And then the cochlea is the roundest spot. And then, of course, we have that cilia. And we know that cilia, as it moves around, helps us because it's vibrating, right? And then that's the part that can get damaged. So properties of sound waves, we know that they are compression waves, also known as longitudinal waves. Sound compression longitudinal. They must have a medium to travel through. The speed of sound is one of those weird things. The speed of sound increases as density increases. So the more tightly packed the particles, the easier to vibrate, or the quicker things can get vibrated, and that sound will travel faster. So that idea that in a vacuum in space, there's no particles to vibrate, that compression wave can't transmit any energy. As I move through at air, sound travels at 344 meters per second, which is much slower than if sound is trying to travel through wood. Thinking about compression waves and the application of like earthquakes and those kind of things. Amplitude is the loudness of the sound wave. It also is from the equilibrium to the crest, or with compression waves, it's the thickness of the compression. So we talked a little bit about that. And of course, wave energy. What's the relationship of wave energy? This was a reading, and we were analyzing relationships. And you can go ahead and skim. This had stopping to thinks, and so I would check out the stopping to thinks and kind of skim through that. With these following graphs, remember we were looking at the relationships between energy and amplitude. And obviously, like when you look at this, you don't even have to know anything. If a book's gonna ask you if there's a relationship, then there probably is. So graph A shows you that as amplitude increases, energy stays the same. No, that doesn't even make any sense. Unless there's not a relationship between those two, but you know that there is. This one shows you as amplitude increases, energy decreases, and that is not true. And then this one shows you as amplitude increases, energy has this curve of increase, and that is the correct answer. So with the reading, you notice that it wasn't a linear relationship, that as the amplitude increased, the energy increased even more. This is a diagram of a compression wave. You can see, like, what's so cool is your eyeballs are thinking that the flow of particles is moving across the screen. And then when you look at the red arrow, so you see the motion of the wave in black is moving from left to right across the screen. But when you look at the particle, it's vibrating back and forth. It's only moving a small amount back and forth. It never has a displacement. It never, so it's moving, but its net movement is always like back where it started. And I love this diagram to help my brain see that particles are not transported and moved through waves. Particles are vibrated, and that vibration passes on the energy. And so we can see the compressions and the rarefactions, and remember the distance between compression and compression is the wavelength. The thickness of the compression is the amplitude. However many compressions there are in a certain period of time is the frequency. So much to see. Like, that's what I love about science. From now on, when you go through the world and you like view things, you view them, the information, with a whole different paradigm. You've got a science paradigm now. This was just a reminder about the speed of sound, that as the medium becomes more dense, the speed becomes faster. This was a reminder about amplitude and energy. And so with amplitude and energy, as amplitude increases, so if I go from 1 amplitude, 1 centimeter to 6, I go from like, what is that, 500? Let's go from 2 amplitude, because 2 amplitude would be easy to read on this graph. 2 amplitude is 500. 6 amplitude is 3,500. So if I increase the amplitude by 4 centimeters, the energy increases by 3,000 joules. Frequency is the number of periods in a number of compressions in a certain amount of time. So if I go from, let's go from 2, we should have gone from 2 to 4. 2 is about 500, 4 is about 1,500. So it's 1,000 times more energy between 2 and 4. Between 2 and 4 here, 2 is like 150, 4 is like 350. So it's 200 times more energy, where this one is 1,000 times more energy. So really, the energy is more influenced by amplitude, but it is influenced by frequency. As frequency increases, energy increases. As amplitude increases, energy increases at a higher rate. Activity 4, noise-induced hearing loss. This is when we looked at the relationship between how loud the sound was in decibels and how much exposure time. So it's not just how loud the sound is, it's also how long you can be exposed to it. So that idea that, if I'm exposed to, typical factory work at 90 decibels, if I'm just around that a little bit, okay. But if I work in a factory and I'm working 10-hour shifts, that could cause a problem for my long-term hearing, that NIHL. Remember, noise-induced hearing loss, NIHL. We looked at graphing data, and at this point, I think I just gave you the graph. And then we were analyzing patient data. So you got different scenarios of different people, and you were trying to develop a plan or figure out who was most at risk. So on this graph here, the 2 variables that we're looking at is sound level in decibels and maximum exposure. As maximum exposure increases, the amount of sound, the level of decibels decreases. So as I increase my sound, the amount of time I can spend, is that what I'm not sure if I said that right. Let me back up. As I increase the decibel loudness of the sound, I can listen to it for less time to manage the health of my ears. So as sound level increases, maximum exposure decreases. And it kind of decreases quite significantly, right? At 90 decibels, I can actually endure 8 hours, but 10 decibels more to 100, it's only about 2 hours. So that's quite a drop in intensity based on how long and how loud the sound is. Activity 5, telephone model. This is where you were able to have a string and you connected those strings and you connected it in cups and you talked to each other and you loved it, and I thought it was hilarious. This is where we introduced the idea of a analog signal, diagram A, analog. When it looks like a wave, that's analog. When it looks like that wave has been transmitted into a code, digital. I found this picture and I thought it was awesome and I wanted to share. This is a group chat. This is Venmo. I mean, not Venmo, Zoom. This is Google Meets. This is the original Google Meets. We're all going to listen and talk to each other. Of course, we have to be pretty close and in the same room. We could just actually talk to each other. But in the scheme of things, what a great picture of learning of you lovely humans. Activity 6, analog and digital technology. Here's where we talked about the difference between the digital signal and the analog signal and the transmission of that. We looked at sampling rate, how if I have the analog, which is this original, that I can take certain information at certain periods of time, and that's the sampling rate. And the more information I take in a shorter amount of time, that sampling rate increases, and I get a better sound from the original sound. We also talked about attenuation, which was as the wave moves through a medium, energy of the wave decreases, and then amplitude decreases, and then I have to amplify it to bring it back up. This was a reading in your book, but I found this on the internet, and I really, really liked it. So the top is analog signals and the bottom is digital signals. So for analog signals, there's some pros and cons. Analog is the original signal, right? Like you and I talking to each other is analog. Now, because my voice is going into the computer is then transmitting it into a file digitally, then it's retransmitting so you can hear it. We have some digital signals that we're communicating with. So if you and I are in person, that's an analog signal. This situation is a digital signal. So the pros of analog is the fidelity, right? Like it's the original signal. It actually sounds like it was supposed to sound. Accessibility, it's easily created. It doesn't cost very much. Recording something analog. The cons is if you want to store information, it requires a large space. Those vinyl records that people collect and had, the records were huge and it only had a few songs on it. The reproducibility, if you wanted to reproduce analog sound every time you made a copy, it would lose quality. And then, of course, the fragility is if that record gets scratched, you've lost a bunch of data. So it's really hard to keep it intact and original. We talked about like the tape on the tape recorder and that strip, that if that thing gets heated or bent, you've lost your information. Digital signals, pros, you can store a lot of information in a small space. MP3s, you can reduce it each time with zero loss of quality. So once you've made it from analog to digital, you can take that digital recording and you can reproduce it as much as you want. You can layer more information together so that you can have overlap. It's easily created and edited. And then there's a caveat over here for cons. Because it's easily created and edited, the mistakes last forever. So as I put this out into the world and put it on YouTube, whatever I say and the mistakes that I make and things that happen, it's there. And people can make copies of it and it's there. It lacks fidelity, right? It's not the true record. It sounds different. This is why people love going to live concerts and not just listening to the CDs or Spotify or all of those. And then you forget about it quite often because there's just so much of it. Nobody remembers like those vinyl records that people collected and stored and still have. So this is a great diagram to make a Venn diagram, pros and cons, what's similar. They're both transmitting information. We're talking with analog and digital signals. At this point, we were using sound waves. Then we switched to another kind of wave. So activity 7 is when we said, okay, we've been doing longitudinal compression sound waves. Vibration of energy is parallel to the direction of motion. Now we're going to move to transverse waves. Transverse waves, the particles are being vibrated perpendicular to the direction of motion. The wave, we did part A where we pulsed the slinky, and part B where we created a transverse wave back and forth, perpendicular. And then we talked more about wavelength, and we looked at the characteristics of the wave and how we label and identify it. With wavelength and frequency, we noticed there's a relationship. So that as the wavelength increases, what happens to the frequency? And of course, we know that as wavelength increases, as the waves get crest to crest farther apart, frequency actually decreases. So this relationship here is the accurate relationship. This one didn't have a red dot in it, but like take this one's easier to see, that this particle right here is just vibrating up and down, up and down, up and down, but the wave is transmitting energy across the screen. The particles are vibrating perpendicular up and down to that. For this, you are going to go ahead and need to be able to label the parts of a wave. So number one would be you could label it the equilibrium. It's the origin of the wave in this diagram, but that's really pointing to that middle point. Number two is the trough. Number three is the wave length. Number four is the amplitude. Number five is the crest. This diagram doesn't show the wave height. The wave height would be from crest to trough. So if I were to measure from the crest at number five all the way down to the bottom where the trough would be, that is the wave height. The wave height is double the amplitude. Amplitude 4. Then we got to wave reflection. We were looking at, now that we were in transverse waves, we were still, using the idea that these waves were traveling through a medium. So light can travel through the air. And when light travels through the air and it hits a different surface, different properties happen to it. If you had an opportunity to do the paper towel tube, it was awesome. It was so fun, where you put the tubes at an angle and different surfaces. So we were looking at how waves, this was sound, reflect, bounce off different surfaces. Some surfaces absorb, some surfaces reflect, some surfaces refract, some surfaces transmit. But this was just the beginning. This was just let's just check. Then we took this experiment where we had a light box and we shined a narrow beam of light across a protractor, lost that word, onto a flat mirror. And when we did that, we looked at the angle of incidence and the angle of reflection, and we looked at different surfaces. For smooth planar surfaces, the angle of incidence is equal to the angle of reflection. If the surface is convex, so convex is that bulging out surface, and if light is hitting a convex surface, it's going to scatter. So if I want my light to be spread out so that I can see a wider area. Ooh, have you ever noticed, I think in Cherry Hills in some places, people have those mirrors at the end of their driveway, or in places that the mirror is convex, it's curved out. And what happens is, as the people are backing out of their driveway, they can see a bigger area because the reflection spreads out the information instead of condenses it. So that is one of the uses of a convex surface, is spreading out that information. And a concave surface, of course, if I shine my light on a concave surface, it's going to narrow where that energy goes. It's the same with sound. And so that question that we asked about the little ears of this cute little adorable mouse, the ears of a lot of mammals are shaped in that concave, so that when the information comes all around, so I have a wider space that I can collect information. And then for that wider space, when I collect information, that information will actually be directed and narrowed into my ear, into my ear canal, and therefore I can interpret information. So the concave surface narrows information and energy. The convex surface spreads it out. Planar surface, the angle it's coming in is the angle it gets reflected. Be careful with reflection and refraction. And then activity 9, we got to refraction. We said, if there is a boundary between two media, and there's not a reflection, the wave was going to go through. And if the wave goes through and the medium have different densities, there's going to be a bend or a refraction. So we looked at information, energy being transmitted. We looked at refraction. We looked at the angle of incidence and the angle of refraction. The critical angle we kind of looked at, but we didn't really go into that so much, so don't worry about that. And then tonal and external reflection, again, don't worry about that. So for this first part, we had a plastic plate, and then in an experiment in class, we would have put like a skim milk in there where the light would definitely be affected when it went into skim milk because the skim milk is more dense than the air. So this white arrow represented my angle of incidence. So I'm going to shine a narrow beam of light 30 degrees up from the normal onto the surface of this piece of plastic. Now, when I do that, will the light just reflect? Will the light just completely go through, transmitted at the same angle? Will the light bend in or will the light bend out? Remember, with light bending in, it means that the medium that it's bending in is more dense with transverse waves. Light. As density increases, speed decreases. That is completely the opposite of sound. My brain doesn't like it. I have to repeat it over and over. I'm going to put that on a note. I'm going to put that on my study guide because it's definitely that situation where it makes sense when you think about the particles and being vibrated and the fact that light doesn't need a medium. Light can travel from the sun to the earth and it does not need a medium. In this scenario, however, we were shining light through air and it hit this piece of plastic and it went into a liquidy here. When it does that, when it changes from a less dense to more dense, the wave actually slows down. And the only picture, the only color arrow that shows it slowing down is the red. The blue would say it stays the same, the yellow would say it speeds up, and the pink would say it completely reflects. There might be some reflection, but it doesn't completely reflect. We get to activity 10, comparing colors. How are the colors of the visible light spectrum similar to and different from each other? So we talked about in that spectrum, that electromagnetic spectrum, we hadn't done that learning yet, but I had talked to you about it, that there's just this narrow part of the electromagnetic spectrum of all the different frequencies and wavelengths that we can actually see color, visible light as humans. And then we learned that it's different for other organisms, but the cells in our eyes are able to, their structure is made so that the information that I process has to be a certain wavelength or frequency, and then my eyeballs interpret those as different colors. I wanted to come back to this. I noticed there was a little bit of confusion when you guys turned in some information on Edpuzzle. This picture here is just the plain old card. So I would give you that card, and that's just the plain old card. These circles have a piece of film in them that has those colors. The white is blank. The white has nothing. The white is my control. The white is saying, I didn't put a filter here. So I'm just allowing the sun's energy to hit the phosphorescent strip. Many people thought the white transmitted. It's not white. If there wasn't a white film, it was blank. And of course, how would you know that? That was confusing, but I'm glad I asked these questions because then I realized, oh crap, they think that the white has a white film. It doesn't. So there's a red film, an orange film, a blank one, a yellow, a green, a blue, a violet. And when I looked at this, of course, I asked you which was going to be the brightest color. Yellow looks brightest, obviously. Of course, your brain, and my brain, wasn't thinking about frequency and energy. In the visible light spectrum, red has the largest wavelength, which is a lower frequency, which is lower energy. That yellow is right in the middle. But the purple and the blue are on the end of the spectrum that has a higher frequency, the wavelength smaller. So that higher frequency transmits more energy. It's so cool. So then this picture below shows you, here's just the plain old card. So this card and this strip are exactly the same. Like this is just the plain old card. When I put that card in the box and I exposed that box to some actual light, and then I pulled the card out and flipped it around, I saw that the control, that light was able to just hit the phosphorescent strip. It's bright. That's a lot of energy went through because nothing was there to block it. That's my control. And the brightest colors, purple and blue. That's cool. That is evidence that shows us about energy of wavelengths in the visible light spectrum. Then we said, all right, well, if we've got energy and wavelengths in a visible light spectrum, what about transmission of information? Transmission of either light, transmission. So we learned that there's things could be absorbed. And when I absorb ultraviolet light, especially, or sunlight, the resulting variable that changes is temperature. So we did an experiment here where we changed the type of film with 3 different types of film. They were different sort of thicknesses, different texture. And then of those 3 types of film, we put them in these little boxes and we put them in the sun. And we allowed them to all sit in the sun in the same location, constant, the same angle, constant. So we changed the film, independent. We measured temperature, dependent. And we noticed that sometimes the information, the sun's energy can be absorbed. It can just go straight through, or it can be reflected. Sometimes when it goes through, it might be bent, so that refraction. But that incident angle, multiple things can happen. So selective transmission of light, which is a transverse wave, is when some light is simultaneously reflected, absorbed, and are transmitted. So all of this can happen. And in our scenario, we noticed that a lot of it did happen. Then we went to comparing ultraviolet, and we took out the thermometers. And I didn't have a picture, so these guys are still holding the thermometers in their container. But we took those out and we put in these UV cards. And we watched how that UV strip was going to change colors. And here's the data that we collected. So film A, you'll notice in these 3 films, information was absorbed. Energy was absorbed in all of them. Well, some of the films absorbed more or less. So if we look at film A, it increased by 15 degrees Celsius. And the UV actually increased by a level of 6. So it's quite a large UV change, especially compared to film B. Film B, the temperature did not increase as much. It still increased, but the UV was really blocked out. So that's kind of interesting. So that absorbing, transmitting, reflecting. C also increased quite a bit in temperature, but based on the UV, it didn't have as much significant absorption as film A. So we're really kind of comparing the 2 variables. So with one experiment, film was the independent, temperature was the dependent. And then the second experiment, film was the independent, UV change was the dependent. And then we put it all together. This is a question I am going to ask you. If you are going to buy some film for a window, your car, something where you really would like to keep the temperature as low as possible when it's a sunny day and to protect yourself from UV. Your data for your experiment's there, but as an added criteria, there's also a cost factor. So when you look at this information, which film would you buy and why? Again, it's open-ended. As long as you support your claim with evidence, you're good. Activity 12, Electromagnetic Spectrum. We had the anticipation guide. I am going to steal some questions from the anticipation guide. You did some before and after to thinking about how your learning and ideas changed. With the electromagnetic spectrum, we see that the waves, electromagnetic waves, which are transverse waves, do not need a medium, so they can travel through the vacuum of space. And they have different wavelengths, different sizes, and different frequencies. So this diagram, You know I love diagrams. Make sure that you can just interpret it and look at it, right? Like some of the questions are just, here's a diagram, tell me what you see. Tell me what information you can infer from that diagram. We also had talked about ultraviolet, and so there we've got our visible light spectrum, and the ultraviolet is more frequent. There's a higher frequency. The infrared was a lower frequency, and then the different filters to see those. Activity 13, where does the light go? This is when we set up an experiment where we changed the type of cloth and we measured the temperature change. So we gathered initial so that we could find final, so that we could see what the change in temperature was. The first experiment we looked at was reflection, part A, where we allowed the light energy to hit the cloth and bounce back up to the UV card. And so when it hit the black cloth, would it bounce back and change the UV? When it hit the foil, would it bounce back? And so which of these would bounce back and change the UV more? And then we looked at the same with the temperature. We had a black cloth, and so which one absorbs the UV, which one reflects the UV? And then, of course, we had a regular temperature for a control. Activity 14, this was the experimental design that I wanted you to do, as well as there was a short video. So in this experiment at school, what we would have done is we would have taken our UV card, we would have taken a plastic film, we would have put it on the UV card. On one side, we put regular lotion, and on the other side, we put a sunscreen. And then we put that out, and we take off the card, take off the film with the sunscreen and the lotion, and we look at, does sunscreen actually block the UV, absorb the UV, take out the UV? And so what's actually happening? That's it, you guys. So if we go back all the way to, sorry, it's really fast, here, your flow of information, it seems like a lot. Like we've done every single activity as best as we could. Questions, come to our Google Meet, ask me some questions. This video will be posted. You can watch it as much as you want. I'm not going to do an ed puzzle, so you can skip, you can rewatch, you can do what you need to do. And I will also post the book. Thank you. I look forward to seeing you soon. Bye.